Okay, so drawing free body diagrams. Um, your your box making a square, little center, all right, point where the rest of our force vectors can come from. So some of the key phrases that you want to look for are at rest or constant velocity. Those things mean that the net force is zero and that everything has to balance. So, weight down has got to equal the normal force going up. And in this case, all right, pretty much every object, guys, is going to have what we will write down as F sub g, force of gravity or weight. Now going upward, again, if I brought this up, okay, you have your force of gravity, gravitational force, weight. You have the normal force, which prevents objects from falling into whatever they're sitting on. We have friction, which always goes in the opposite direction of motion. Your applied force, which could be a push or a pull. Tension, net force. Other common forces would be air resistance, and potentially like a spring force, but we're not going to get into spring force right now. So you have to see that this thing is at rest, which means the net force has to be zero. So that means your vector going down has to be the same length as your vector going up. And you can show that by drawing this kind of little equal symbol right there. And we, right here, this is our F sub n, your normal force. Now, there's no other forces acting on this because they're not telling us that this thing is getting pushed across the top of the desk, it's getting pulled, or anything like that. So those are the only forces that we're experiencing right here. Now, number 4 says an egg is free falling from a nest out of a tree. Neglect air resistance. So we're basically in a vacuum. Draw a free body diagram for this situation. Okay, so this square represents our egg. The egg obviously has mass, so has weight. All right, force of gravity, gravitational force pulling it downward, F sub g. But if there's no air resistance, is there anything going upwards against it? No, there's not. So this is the only thing that you would see. And since this is the direction of the net force, which is downward, since the net force is going downward, this object will accelerate downward, which should make sense. If you drop a pencil, drop a pen, okay, yes, there's some air resistance, but it's not enough to kind of to balance out what the weight of the object is. So it will accelerate in the downward direction. Excuse me. Now, flying squirrel here is gliding from a tree to the ground. When you see constant velocity, all right, constant velocity and at rest means the net force is zero, everything has to balance. So those are some key little phrases that you want to keep in mind. Those are some key little phrases that you would like to keep in mind. All right, so it's flying or gliding down to the ground. Now this time it's saying consider air resistance. Well, we know that we are going to have gravity, force of gravity on the object. But what does it say? Constant velocity. Again, what does constant velocity mean? That the F net has to equal zero. So if I have something going downward, I need to have a force going in the opposite direction and be the same size. So like here to here, here to here. Okay, and what were we going to call this? We're going to call this air resistance. So F subscript air. It's our air resistance. And if you want to show that these two little vectors are equal, we're going to put like a tiny little equal sign in them. All right, cool. So that's basically just telling me that, if this was 10 newtons and it's falling at a constant velocity, well, the air resistance that it's incurring also have to be 10 newtons. That's essentially what's going on there. Now, in this case here, you have a rightward force. Now, there's a couple different things going on in this one. All right, you have a rightward force moving a book across a desk with a rightward acceleration. Consider frictional forces. Ignore air resistance and draw a free body diagram. So if this is my desk, this is my book. Okay, first thing you can always draw in is, say it, F sub g. All right, gravitational force, its weight. Now, in the problem, does it say anything about the object moving up or down? So if that's the case, and you think about it, this is where guys like real life situations do come into play. If you have a book sitting on a table, the book is not just going to be floating upward, rising up out of nowhere, or falling through it. So we are going to then use our pre-existing knowledge here, say, okay, well, the normal force that is preventing the book or whatever to fall through, they have to be equal. They have to be. Why? Because there's no motion in the upward or downward direction. So those two gotta be chilling. They gotta be equal. Okay, well, they said that this thing has a rightward force applied to it, and it has this, a rightward acceleration. And then to consider frictional forces. Okay. So we have a rightward force being applied. So we're going to draw an arrow decent size, and we're going to call that F applied, APP, which stands for a push or pull force. Now, guys, if a net force is 0, what is the object going to do? Is the motion going to change?
No, stay the same.
No, it stays the same. In this case, they're telling us that it is accelerating. So the only way you can change your velocity or an acceleration, have an acceleration, is by having a net force greater than 0. So, and there's another little trick or rule that, all right, the acceleration goes in the direction of the net force. All right, so acceleration goes in the direction of the net force. Remember, there can only be one net force. It is a singular force. So since that is being told, or since we have that piece of knowledge now, we know that there's a rightward force being applied, and it's accelerating to the right. So if I just did a small little sketch over here, all right, since it's accelerating this direction, I know that my F net has to be to the right. It has to be to the right. So if that's the case, based off of the examples that we were doing earlier, that means that this rightward force needs to be greater than the leftward force. So we're going to have a leftward force, but we're not going to make it as big. All right, it's not going to be the same magnitude. It's going to be a little smaller. All right, and there's one of the forces that we talked about that always goes in the opposite direction of motion. So guys, you like slide your hand across the table. All right, what is kind of preventing it from moving, or what kind of slows it down? Friction. Very good. So we will call that F sub F. That is, all right, that is our friction. And we also need to know that friction, it's a little side note, if you didn't have this. Friction goes in the direction opposite of motion. So if this thing is moving to the right, by telling us that it's accelerating to the right, that means friction would have to be drawn to the left. They could have said, okay, this thing was getting pushed to the left, and then in which case friction would be drawn to the right. Now, up and down, we kind of put the little equal signs here telling us those are balanced. So we're basically pretending like they're not there. And just like we're looking at the size or the magnitude of the vectors, the rightward arrow is larger in size. So that is going to be telling us that, yeah, it's going to have a larger number. So if we just said, okay, like, well, the friction force was 10 newtons and the applied force was 20 newtons, what would my net force be? If normal force and gravitational force are equal to each other, if you have 20 to the right and 10 to the left, what would my net force be? 10 newtons to the right. All right, so the rule is add in the same direction, subtract in the opposite. So they're opposite directions, subtract, and then the net force will go in the direction of the, all right, whichever force had the larger magnitude to begin with. So 7, 8, and 9, you guys are going to be able to, I want you guys to do on your own, but I do want to take a look at 10. Now, just again, a couple things. Constant velocity, what does that mean about net force? Guys? Constant velocity means the net force is going to be? Yep, which means everything has to? All right, balance out, equal out. Again, same thing here, constant velocity. So that should help tremendously when making these free body diagrams. Okay, they're talking about a rightward acceleration here, but this one should be similar to one that you've already done. The only one we're going to look at right now is number 10. So they said a car is coasting to the right. Car is coasting to the right, and it is slowing down. So they want us to draw a free body diagram for this. Okay. So if you were to, let's say, just kind of slide your binder across the desk a little bit, you push it to the right. All right? You gave it a push force. Now, as soon as you let go, you're no longer applying that push force to it, right? You're not making contact. Now, if you give it a strong enough push, it's still going to move to the right without you touching it, right? But is it going to be going as fast? No. What happens to it?
Slows down.
It slows down. Why is it slowing down?
Because of the friction.
Very good, because of friction. All right, so thinking about a car, okay, you take your foot off the gas, all right? That would be like taking your hand off of the book, all right, of the binder as you go to push it. Well, it was originally moving to the right. It's still moving to the right. But we definitely can draw in our two forces here, gravitational force, all right, the weight of the object. Obviously, it's not falling through the road, so we have to have a normal force that is equal to the gravitational force and opposite in direction. Now, let's say you're driving and you take your foot off the gas. You've just taken off your applied force. Now, let's say that's gone away. All right. Is the car going to go forever? No, you take your foot off the gas. Most of you guys have, all right, done your 6 hours or have your license. What happens if you've ever just like been driving, like you get off the road, you come down your street, and I don't know if I'm the only one that's ever done it, but like I'll get up to 25 miles an hour, and then I just take my foot off and just see if I can make it all the way to my house, from that, or like 30 miles an hour, and then let go of the gas and just kind of coast down. Well, I'm no longer applying a force here. I'm no longer applying a force, but what is happening? You all realize, right, based off of real world life examples, all right, and experience that you're slowing down. Well, that means that something has to be pushing you in the opposite direction or pulling you in the opposite direction, causing you to slow down. So in this case, all right, our friction force would be drawn to the left. It would be drawn to the left. So in this picture, all right, yes, the object is still, even though, all right, the problem is telling that this thing is moving to the right, you would have a hard time looking at this and telling me it's moving to the right without reading that problem. What you can say from this, though, is that the net force would be what? In what direction? If top and bottom are balanced.
Up and down. Wait. Top and bottom.
Up and down are balanced. So what direction, what is the only other force remaining?
Right. Left. Right, yeah.
This force, right?
No. That's not right.
So in this case, your net force would be to the left, which is causing there to be an acceleration to the left. In this case, a deceleration, a slowing down. So remember, if a net force is 0, everything has to balance, and the object is going to maintain whatever its motion is. The motion is not going to change. So if it's at rest, it's going to stay at rest. If it's moving at a constant velocity, which is a straight line, constant speed, it's going to continue to do that. But if you do have a net force, the object is going to accelerate in that direction. Now, Kate, again, this would be like pushing your binder across the desk to the right. As soon as you push and let go, you no longer have this force. This, as soon as you let go, as you push, goes away. But friction force is going to be acting on it. Now, it may start off really high, but as the speed decreases, it gradually gets smaller, 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 and then if you come to a complete stop, well then that force is then basically gone at that point, and then you would just be left with this. All right? So you guys are to do numbers 7, 8, 9 for homework, which you have time to do in here. And then you have the front side, which you should be very familiar with how to do. All right? And then these problems here. Understood? All right. Very good.